Today we're focusing on two key questions. First, why do diffusion models often produce local instability in video generation, such as flickering, misalignment, or drifting details? Second, can popular inference timescaling techniques, like adjusting CFG scale, changing the noise schedule, or modifying sampling paths, fundamentally solve this issue? Let's start with the first question. The core idea of a diffusion model is to start from a noisy image and gradually denoise it to reconstruct the target. In image generation, this process happens once per image, so local variations are relatively contained. But in video generation, every frame is sampled repeatedly, and the same local region might be independently regenerated at different time steps. That's where things start to break. Local incoherence emerges. For example, faces suddenly shift positions, background buildings morph, arm lengths change between frames, or hats randomly disappear and reappear. These are classic signs of unstable local denoising. The root cause, diffusion, is a Markov process, step-by-step sampling with local updates and no explicit memory of global structure. Each step is a stochastic patch-up. There's no inherent mechanism to ensure temporal or structural consistency. So, can we fix this with smarter inference time strategies? That's our second question. Many recent methods try to mitigate this using inference time scaling techniques, such as increasing CFG scale to strengthen prompt guidance, though this can also cause detail distortion or overly rigid results. Modifying the noise sampling path, like switching to DDM or DPM solver, or tweaking the initial noise and optimizing the direction of conditional embeddings to improve output stability. These methods do help to a degree. They reduce local fluctuations and improve controllability, but they all share one major flaw. They fine-tune sampling after the fact rather than solving the structural issue at the modeling level. Put bluntly, the model never truly learned fine-grained semantic alignment in the first place. Most diffusion models are trained to learn a conditional distribution like PX, that is, generate video X based on text Y, but they don't explicitly learn which word maps to which object or which structure belongs to which time span. In other words, the model might understand you said cat, but not that the cat should be on the left, wearing a hat, waving its paw. So trying to control these structural details using CFG scale, noise seeds, or sampling tweaks is like expecting a model with fuzzy prompt understanding to become precise at inference, which simply doesn't work. At the end of the day, the issue isn't just about inference, it's about how the model was trained in the first place, with objectives that lack structural and semantic grounding. To truly improve controllability, we need to start at the modeling stage. Embed structural relationships, model fine-grained semantic alignments. The model shouldn't just generate content, and it should understand what should appear, where, how things relate, and whether they meet the intended semantic constraints. And that might be the key direction for the next generation of controllable video generation models.